I'm presenting on today was a project that I did last semester at Columbia, and we titled it Solving Linear Algebra by Program Synthesis. There's a lot of fancy words here, but as we get into it, I'm not going to go into every single slide because you'll see these are very wordy and it was more for my like final project, but you'll get the basic idea. And I do want to talk about some like motivation as well as our methods. Yeah, so to start off, in the last week, we talked a lot about machine learning and a lot about like supervised learning, where we kind of have to feed like the algorithm, maybe like a bunch of images or a bunch of examples before it can learn like what something is, whether it be like a dog or a cat. But if you think about it, like for us, like a child, honestly, we probably haven't even seen like 10 million or like 10,000 images of a cat or a dog in order for us to recognize what that is, right? And the same applies to like a 10-month-old child, right? They don't have to see like 10,000 images of a horse before they're able to look at maybe like a painting of a horse or something that represents a horse and be able to identify it. So what's kind of happening here goes into like deep learning as well as transfer learning, and that idea that we can make machine learning even more like how we work. And instead of just feeding it a bunch of data or a bunch of examples and have it learn, it can kind of learn the way that we do. Another example is like when we take courses in school, we would take maybe like pre-algebra before we take algebra, as material often builds on itself rather than, we just see 10,000 algebra problems and then we try to solve them, right? So speaking of algebra and math problems, something that we've noticed is that machine learning and AI is actually surprisingly bad at solving math problems. So I linked the article. It is like a little bit old, that it's been like it was from last year. So there have been a lot of changes since. But there's like 7 different areas that they talk about with that AIs don't do as well in. However, the one that you can see that they're focused on is that neural networks are surprisingly bad at math. Right. So this is really surprising because we'd think that, computers would be better at math, right? More efficient or like better at crunching those numbers than we can. But they found that neural networks are actually not as good at solving math problems as they are at something like maybe like a natural language processing, where they're like mimicking a human response. Okay. So kind of with that article, as well as just like this thought process that like maybe it doesn't have to be so hard to teach a machine to learn something. We get into like what we use. This is our long intro, but I'll just stop at the method slide. So when we last week when we did the NLP lecture, one of the activities that we did was with TechSynth. If you had me in your if I was in your instructor, so here's TechSynth again. I'll link it for everyone again if we forgot or if we want to play around with it. So TechSynth was the playground where we could enter like part of a sentence or some words, and the machine would be able to finish that sentence. And if you were in my section, again, I mentioned that TechSynth, or at least this playground specifically, uses GPT-J. So in my research, I've done research in a lot of different like language models. So GPT-J is one of them, and the one that I'll be talking about or with my project was with GPT-3. But again, GPT-J, you see it has 6 billion parameters. GPT-3 has 30 billion parameters. Again, the number of parameters doesn't necessarily mean that it's good or bad. It's more just what like these parameters are better for solving certain problems than other problems. So this was TechSynth. We remember how it worked. You can put in a question or even code, and it would be able to complete it. So what we used for our research was GPT-3 on OpenAI. So I'm also going to link this. If you can, it'd be really great if you want to, especially if you're like interested in large scale language models. OpenAI has like a lot of these. You'll see I'll try some, but you can see on the right here, there's all of these models that you can test out and try and play around with and see how the machine reacts. And you can kind of like fine tune these models as well, which is really cool. You should be able to get access. The last time I know my research team, some of us had problems getting access to this, but I believe if you just put like, oh, you're doing this for research, I think they give like a few credits. But yeah, so this is really great to explore, and this is what we did our research on. Okay, so now that I've kind of like introduced some of the tools that we're using, we'll get into what we actually did. So again, going off of that, like, oh, why is it so hard for neural networks to learn math? We wanted to test the capabilities of it. It does have like the capability, like, if you just put in like a simple addition. But one of the issues was with we were trying university level questions, right? So our professor actually did find that, where is it? Okay, yeah. Jory was our professor. Here's this third point under related work. But he did find that using GPT-3, especially on OpenAI, which I will test in a moment, did perform better than what was in that article. So he already found that there were improvements. But my team wanted to try out something called few shot learning. So again, let me introduce what we used. So we used questions from 4 courses. We used Stat 110, which was a Harvard probability course. We used questions from 1805, which was an MIT probability course. We used questions from 1806, which was an MIT linear algebra course. And we used COMS 3251, which is a Columbia Columbia linear algebra course. My project was on linear algebra because I focused more on linear algebra. My partner mostly did the probability questions, but they overlap and the process was very similar. So what you can do with TechSynth, remember we would ask it a question and it would be able to answer or just from that context answer. So what you can do, so here's our charts with all of the question pairs that we tried. Oh, it's not loading. Okay. But maybe we can like do the same thing with TechSynth here, right? You can ask it a question, see how well it does. This is a linear algebra question. I believe, again, if you were in my class, I ran this as well. You'll see that, well, first of all, they have like a few, it'll give you different ones. Okay, well, this is giving the same, but you'll see that it does kind of have the background behind like what a vector is. It's giving some of the like information on what a sum is, what a difference is, but it doesn't really go beyond this, right? It's not giving us the answer to this, and it's definitely not drawing a vector, right? So let's try this again in with GPT-3. Oh, okay. See, I've actually hit my limit, so this was the problem. Okay, so what'll happen here, I'll just describe it, and I think it's in our methods as well. So that was the problem that some people were reaching. They give you a certain amount of credits, and then like if you hit that credit limit or if it's like outside of the date range, I think you like can't use it anymore. But this is a different problem. But if you entered like this is what I was entering in the in OpenAI or GP3. You would enter it like this, like I said, with the 3 quotes that I had. This is just like the format that they take it in, but it would output a piece of code instead. And this is Python code, and you would actually see that when you run this code in Python, it actually does solve this problem. It actually computes this this linear algebra problem. And so that was really interesting to find, but we found that it didn't actually work with all of them. So we wanted to improve upon like initial findings that this did work, but we wanted like higher accuracies. So what we did is we tried few shot learning. So the difference between zero-shot learning. So zero-shot learning is where the model doesn't observe any previous context. So that's just putting in the question as it is, not giving it any additional information or context. But few-shot learning is giving the model a few examples to learn from before you give it the final question that you want it to ask. So this goes off of what I was saying earlier, where, we have like pre-algebra, before algebra, where, like a 10-month old child would be able to know like maybe an algebra, not an algebra question, but like a math question, not because they did 10,000 questions, but because they built off of prior knowledge that they did. Um, but you'll see here that we have this question, except this time we give it the answer. So all of this actually goes into what I was showing you earlier. So hold on. So instead of just putting 1 here, we would have like 1, and then we would have, actually, I can put this out. It's not going to do what it is, but. So instead of putting just this, which would be zero-shot learning, we would do like this. We would give the answer for this, and then we would put in like a new question. And then we would submit and ask and see if it would output an answer. So this is not going to run for me, unfortunately, because I did run out of credits. But what would happen is, now we have this methods again. It would again output code, and this code, this Python code, that if you ran it in a compiler would actually be able to calculate the answer to this linear algebra question. So we saw that with this method, we had more accuracy. We were able to solve some of the problems that couldn't previously be solved with zero-shot learning. And so here's like the table with our kind of like our results. We saw that there was the best accuracy, or the most improved, was when we did a reverse order, which is like when we so we also did like we would rank like how similar the questions were, and this is just like with like a cosine similarity like equation. But when we did like reverse few shot, which is where we would put like a question that was further from it and then a question that was closer to it, and then put that answer, the machine was able to learn like, oh, we're getting closer and closer, like this next problem has context for this next problem, and from that it was able to like more accurately solve like a new incoming problem. So this again is like what I said before with like why we take like pre-algebra before algebra, or why we have like courses that build on each other, as well as like just when we learn in general, we usually take context from what we know before and apply it to like the next problem. Yeah, so then for like a conclusion and just like what we found, we definitely found that fine-tuning like GPT-3 in this way and kind of giving it few shot learning and giving it more examples before it got to the final problem gave us a much higher increase in accuracy. And something that we wanted to do later or improve on was, so the courses that we took were just kind of like I guess I would say they're like parallel, right? They're all like intro probability. This doesn't say intro, but I'm pretty sure this is the intro probability course at Harvard. And these are like intro linear algebra courses, but we wanted to do something that was like maybe like a intro linear algebra, and then we do like an advanced algebra and kind of take few shot questions from the intro class and see if the machine would be able, or GPT-3 would be able to solve the more advanced linear algebra questions. And this would be like, this next step would be like what I said previously, like more clearly proving that like you need like pre-algebra before algebra, just like how we learn. Cool. Yeah, so again, did I link? Yeah, these were all the 3 things that I want to link. I just think this was really cool. I learned a lot, and this was especially surprising when we started doing fuchsia and we saw just how much the accuracy increased. It was really like it was really shocking to see, but also it just made a lot of sense that it works just like us and how we would learn. And so even though this was released in September, we've come a long way and seen that we can actually make neural networks work pretty well with math problems. Cool. Any questions?